Probably this will be second law. So let's see. So we know that first you have our first law, and you know that you can convert heat. Sorry, you can do it the way down. You can convert work all the way to heat completely, right? 100%. Right? A classic example is, it's not the Joule expansion, but the classical Joule experiment, right? I didn't talk about that, but it's discussing the proof. Right? So this is how we actually calibrate. Actually, this is how people know at that time that heat is not another substance. Heat is just a form of kinetic energy, right? There was an experiment discussing the book. You know, you have a water container with a bunch of paddle here, and then this is first of pouring, and you just throw in mass, and you use it many, many times, and you realize that the temperature increases. Okay. I didn't discuss this because I thought it's not necessary. So the question that people asked at that time is that, can you see the reverse process? So this is doable. Can you actually convert heat to work? Okay. So it's a question like this that preoccupied a lot of people early last century, right? I mean, this is still, if this obey the first law, right? The first law satisfies the first law, you can convert all your work into energy, right? And why not the reverse, right? It still satisfies the first law, right? And it turns out you can. Right? It's not possible. Okay? And somehow, I mean, I'm not going to give a historical discourse on this, but it was made into a law later on, actually, by Clausius and Kelvin. The two statements of the second law. This is the second law. It's the Kelvin statement. In fact, we call it Kelvin-Planck. We call it Kelvin-Planck, I don't know why. But it says no thermodynamic process whose sole effect is to extract heat from system and convert it all work. So that process is not possible. And this is called the Kelvin statement. Another statement that was also discovered in that around the same era is the statement by Clausius. Here, the reason I'm writing this down because this is important, I suppose, but this is exactly also in your textbook. No thermodynamic process. The caveat, of course, is sole effect, right? Which sole means in which the sole effect is that heat flows from the reservoir reservoir at a given temperature to the reservoir are. At the okay. So this is the true statement, and we'll show later that this is equivalent. So also, we know that the reverse is possible, right? The reverse of the quasi-statement is possible. You can always
So what about like you have that isothermal experiment or something like that? Yeah.
Yes, yes.
And
Yes, but the thing is that that's a very good question. I was thinking that one of my students will ask this question that still last night. This process says a sort of fact, right? So basically the system has to return to its same configuration as at the beginning of the process.
oh,
So what you have, your question is this, right? It's a very good question. This is the thermal dot, right? And then this expand, right?
yeah.
So it's inverting, and then there is a heat transfer, and then this will work, right? But at the end of the day, the system is in a different place, right? Meaning that the system is not back to its original condition. The piston is over here, right? So if you want to bring back the piston to its original position, then you have to do work. Right? You have to do another work, right? And then heat will get transferred back into the feedback. Right? And because nothing is ideal, eventually this work is actually greater than that work.
Question.
Yes, sir.
Going along that, does that mean that is it possible to have a case where, like even though the final position of the piston is different, like all the heat that was transferred from the bath ends up being work, or is that also possible?
Oh, this is possible. You can have this process. You can transfer heat into work.
Like 100%.
Yeah, but the system will be in a different place. Yes, yeah. So this is why this statement is important, right? It's all a fact. One of the preoccupation of people in the early 1800s is that you don't really do it anymore, right? There's no startup that's like trying to do this. People 200 years ago they want to know if it's possible to construct a perpetual engine. That's one of the preoccupations in the early 1800s. Is there a way to actually make a perpetual engine? Right? So in that kind of frame of mind, people eventually came up with that this general law, right? In the process of studying engine. So the opposite of the quasi statement, I mean, it's also possible if I have, you can also, there's a process that can take you from a high temperature, right? If you have a high temperature, T1, T1, then you can take the thermodynamic process that can take you from high temperature to low temperature, and that's fine. Okay. So let's see. The first person to realize this is actually not Kelvin and Planck. This is actually done by Carnot. Carnot was an engineer, or a mathematician in France, and he studied with names that you will encounter later in the semester, Ampère and Poisson in Paris. But his father was doing a lot of study of energy, and he saw his father work in Germany and something, and he actually was the first person to realize that you can derive general law in this case based on a study of ideal energy, right? So let's look into energy. So an engine, there's a lot of words here. I mean, should I just say it to you or write it down? all this is an idealized mathematical description based on abstraction of a real engine. At that time, you have real engine from the Watt steam engine, right? And that's what his father was doing. Right? So an engine convert thermal energy the mechanical work and after the completion of the work return to its initial condition. So an example says a steam engine. And there is a caricature given in the book that you should read. What I have here is a turbine engine with initial control. Okay. So what you have is a boiler. Okay. And then it rotates a turbine. And then there's an exhaust. And this is a condenser. Right. And this is a temperature T high. This is a low temperature. So the steam, pushes against the turbine, rotate the turbine, does work, right? And then we must create a pressure differential for the turbine to rotate. So you have to lower the temperature so that the steam condenses. Okay. So Carnot had the insight to actually look this as an idealized process of something that looks like this, right? This is drawn all the time in your book. Temperature T high and temperature T low. Right? So you have a T high work, right? All this quantity is positive, by the way. If it's negative, then it's the reverse. I mean, an engine doesn't have to be like this. This is an idealization by Carnot, right? An engine, you don't have to have a reservoir that's always high, and it doesn't have to have a condenser that's always at low. Even for an idealized system, it doesn't have to be that way, right? That is idealizing the converter, right? They take an engine like this, idealize it, and this is a caricature of the control. Right? And then later on, at the end of the day, he can construct any engine, any ideal engine by a series of engines like this. Okay? As we will see. Right? But first, let's define a few quantities, right? This is clear so far. In particular, right? Say in this case here, then the boiler will is at a high temperature, the condenser at a low temperature, right? There is a heat that it's not quite clear here because you have this pressure. It's slightly different, but if you look at your steam engine example, it's probably more clear. There's a heat that goes into the engine and then generate work, and then you pump the heat out into the condenser, right? And let's define a few quantity, something that can naturally define, say, its efficiency. E, right? And this is defined as the work that the engine can do, right? Divided by the amount of heat that enters into the system, right? From the first law, first of all, we know that you must have conservation of energy, right? Therefore, QH, this is QL plus W. Okay, and the efficiency is just, if I just do the math, it will be given by 1 minus QL over QH. Okay, since there is no process based on this new statement, which we'll do later, no process, or we'll elaborate later, whose sole effect is to transfer all heat into work, right? You must have exhaust, right? Therefore, efficiency is always less than 1, right? Because QL is finite. That's a statement from Kelvin, right? Actually, there's also a statement by Carnot, 20 or 30 years before. And the reason I keep on mentioning Carnot is because all this discussion here is based on Carnot. So, let's see. First, so that's the discussion on any engine. Carnot wants to discuss an ideal engine. Or a perfect engine. Okay? So in this case, it has to be frictionless. Right? Otherwise, you lose energy to things that you cannot account for. Right? And then things have to be quasi-static. Right? Meaning at every point in the process, because this is just a mathematical discussion, right? At any point in the process, you can always define your system thermodynamically. Right? So slow enough that E, pressure and temperature and whatever is well defined. Right? So in the PV diagram, say, right? Every single point in that process, this is any process. Any process. It's always well defined along the PV curve. Right? The next thing, it has to be reversible. This is very important. Okay, reversible means that whatever process, if a process goes this way, you can also reverse it. Right?
So when would it ever be like too fast to define it?
Sorry?
When would it ever be like too fast to define it?
Too fast to define. Too slow enough that then the whole thing is not quasi-static. Then you cannot.
Give an example of what would not be quasi-static.
Oh yes. I want to give an example. That's the point, right? So what is the difference between quasi-static process and reversible process? Say quasi-static process. Right? Anything that's slow enough that all the macroscopic variables is well defined is quasi-static by definition. Say, for example, we didn't complete the discussion last week, the field expansion, right? The Joule expansion. So there's a gas here, and there's almost no gas here, and you make a very small hole, right? And you slowly lead the gas in that direction, right? At least on this compartment, right? Things are always kind of quasi-static. Right? As the molecule leaks out, you stabilize all the time. Right? Another example of quasi-static, this is a Joule expansion. Another process is, say, if I have two systems at temperature T1 and T2, right, and I have a partition so that this is almost insulated. Q dt is very small. Very slow heat transfer from system 1 to system 2. Right? This is also quasi-static. Right? At any point in the process, as this temperature goes from T1 to T final, and T2 goes up from T2 to T final, at any point in the process, all the thermodynamic variables will be defined. Right? Slowly down. Right? It's not true if suddenly, if this is actually a conducting surface. Right? Then you have a lot of differences. The temperature is not well defined. This is finite difference. And so the cooling happens very fast. Pressure might change in a trivial manner, and then you don't have a quasi-static process.
What's the difference between quasi-static and reversible then? Because I
yes.
feel like I read that like reversible process have that really slow.
Right. Yes. Reversible. So this is reversible is a subset of quasi-static. Right. So in this particular case, these two examples, is it reversible or not? How about the first example?
No.
It's not, right? The first example is not reversible. Once the gas escapes to this side, no process will take it there. Okay? And on the second example, it's also the same. Right? The second example, once they thermalize in GF, right? And this is actually the statement of Clausius. They cannot go back in the other direction. Right? It's quasi-static, but it's not reversible. Okay? So what is a reversible process? The definition is that it's just the definition of the word. Then you should be able to change the direction of time and everything, if it will be okay again, right? So say if I have two systems at the same temperature, okay, and the thermal contact. Okay. If I just raise this by dt, right, then heat will flow down. Okay? But I can always reverse it, right? And if I increase this differentially by dt, this is all mathematical, by the way. This is almost like in 7a when you have a frictionless pulley and all that, right? And if I lower dt suddenly differentially, then heat will come back down. And this is a reversible process. This is not true if this is just almost a special case of that one, right? If there is a finite temperature difference, it's not reversible. Right? Because if T1 minus T, T1 minus T is finite. Then it's only quasi-static if you make this almost insulating, but it's not reversible. Okay? If they're the same temperature, then it's reversible. I can raise it differentially, heat differentially flow one way, lower it differentially, heat flow the other way.
Wait, so I'm confused because the reversible process, like you can heat it differentially, like you could I guess imagine doing the DT like a lot of times, then it'll actually raise a finite amount, right?
Yes.
So then if you look at the other case, then
Yes,
can't that be like reversible as long as you consider?
Yes. This is all very process dependent. That's a very good point, right? So if you do this, just like when you do differential equation, right? You build the finite difference through differential process, right? Then yes, but in the process of doing that, you have to introduce many intermediate steps, right? And that can be done, I think. Right? The simplest way to understand reversible is if I can somehow plot it on a PV diagram. Okay? Then I can always go back. Okay?
Because temperature is constant?
Not necessarily. Right? Meaning that you have to go through the process to make sure that that is happening, right? Mm-hmm. And then a lot of the time it's not easy. This is an idealization. And suppose if you see isotope, right? So if I do things like this, right, then I have to change the temperature differentially every time. Right? So I have to introduce heat back of all this differential temperature difference. Right? So it's only possible as a limit of a mathematical idealization. Okay. Another example of this is if you're doing work, right? This is the example that we talked about earlier. Okay. Isothermal expansion. Okay. So you can do this you have to do this quasi-statically to make sure that the pressure is always well defined, right? But if you do it slowly enough, the whole thing is reversible also, right? So you can expand this a little bit, right? But you can push back. Everything just reverses itself. If you do it on the PV diagram, it's the simplest PV diagram that is in isotherm. Right? I'm over here. I can just go along this curve, and I'm over there, right? But I can always go back. Okay. If the process is all well defined with an equation of state, you can always go back. But not all processes are like that. In fact, most processes are complicated, where to even talk about this, you have to go through an infinite number of steps, right? So that was the things that preoccupy Carnot, how to build an engine that is actually ideal, right? It turns out there are you can build it out of these two processes that you already learned from last week. Isothermal processes. Right. That's very easy because if you have a piston, right, in some kind of a bath at temperature T, right, then if it's quasi-static, you guarantee that's reversible, right? Also, and the other one is adiabatic. So there was a reason that we did all that last week. It's not just a nitro exercise, right? It's not just for problem solving. If it's adiabatic, right? Distance. There is no dq, right? And you know this process from last week on the PV diagram. Right? This the power of gamma is constant. Right? In this case also, you don't have to do anything. As long as things are quasi-static, right? As long as you move the piston slowly enough, right? Then you just trace this curve, right? Because you don't have to worry about heat back in this case. There is no heat back to worry about because we insulate the whole thing, right?
Why are there arrows going between the inside to the outside?
Oh, sorry.
Okay.
Yeah, right. That's what I'm trying to say. No heat transfer.
Okay.
Right? So it's very easy to do. You can imagine just doing this mathematically on paper. That's all there is, right? Same thing with isothermal, right? Isothermal, in an isothermal process, Q is 4, right? You don't, unlike any arbitrary process where in order for this to happen, you have to have infinite number of heat back, right? Because going through this, right, if I have an engine that goes through a path like that, it has to go through many isotherms, right? At every single isotherm, it has to be in some kind of a thermal contact. So you have to have an infinite number of heat back, right? You see my point? These are the two processes that you don't have heat yet. Okay. So how do you build an engine based on this? Okay. It turns out you can, and this is what Carnot did. It's called the Carnot engine. So on a PV diagram, that's the easiest thing to see it, right? Remember, just to remind you, this is an idealized engine that Carnot talked about. There's a T high, there's a T low. This is the system that does work and then come back to the same initial state. Okay? T high, T low, and then work. Okay? You want to create a situation where the, say in this case, isothermal expansion, right? Heat transfer to the system, it does work, right? Okay, and then you have to somehow bring it back, right? And there is two temperatures, one T high and two, and then there's also a heat jump at temperature too low, right? So let's draw that in the PV diagram. So this is T high, this is T low, right? These are the two, you're given only two heat factors. Right? T high, T low, okay? And then you have this system of system S, right? So the first thing you do, suppose you are over here, right? In some initial condition, initial state I call A. Right? This is exactly a discussion in Feynman, I think. So what you do is you do an isothermal expansion. Right? So what does it mean? You go along this path. I always have a chart of a different color. Right? You go along that path. Okay? So it's very easy. You put the system with TH, let it expand, right? Along this way, until you reach point P. Okay? The system is still at T high, right? You take it off from the reservoir, right? And you let it expand further, right? But in this case, there's no more heat transfer, so it's doing an adiabatic process. It goes from this point to that point. And what is PG gamma equal constant? That takes you to point C. Okay? So it will expand further, right? And at that time, because there is no heat transfer into the system, the temperature of the whole thing drops, right? When the adiabatic process causes the temperature of the system to drop all the way to below, then you stop the expansion. Right? And then you put the system back into TL, right? You put it back here. In thermal contact with TL, so that it contract, right? You expand, and then it contract. It contracts along the isotherm because it's in thermal contact with TL. Until you reach point T, right? And of course you have to do this mathematically. So at some point T, that's appropriate, you stop, right? And then you take it off from the heat bath, right? And you let it contract even further. So it traces an adiabatic contraction like that, back to the original point A. Okay? And this is called the Carnot cycle. Or it's also called the Carnot cycle. Okay? So, let me do this. This is the expansion, this is the contraction, right?
So the external work is done on the adiabatic processes?
The extra work is done also on capital properties, you're correct, yes.
Okay.
So to work the two-part work, look at the system isothermally and adiabatically.
Work done by the system adiabatic?
Yes, yeah.
But work also done on the system adiabatic?
Later on the way back, right?
On the way back, that's
Yeah,
what
on the way back, then you have to push against the system to work, right? On the way back, you're doing work isothermally to compress the system, and then adiabatic. Question? Okay. So in this case here, remember this is the idealized engine that he had in mind when he was studying this. So how much is the amount of work done? So there's a work done by any expansion, right? There's positive work by the system, and then there's also work done on the system by the external engine, right, on the way back, right? So the total work done is this area here, right? This is total work done by system. Okay. And how about QH? QH only happen over here, right? Isothermally, at the beginning, from A to B, the piston is in contact with TH, and TH transfer QH into the piston. Right? So QH is here. Right? And where is QL happening? QL is happening over here. Right? As you're compressing from C to D, you're doing it isothermally. So the piston is in contact with the reservoir. Right? So as you push against the system, right, it transfers heat QL into the reservoir. Right? And we just need to calculate the efficiency. So you have to use this. Okay. So that's what we're going to do next. Okay. So let's see here. That's what we want to calculate, right? We want to calculate the efficiency of this particular reversible engine, right? Carnot engine, this engine, right? And then, within whole classification of engine, you have a reversible engine, and one type of reversible engine is Carnot engine, okay? And we want to calculate the efficiency. And this is all just algebra from here on, because you already know how to solve this problem. Right? We did this last week. Right? Okay. First of all, just put everything in writing. So process from A to B is isothermal. Right? So what you have, the pressure at A times the volume at A is equal to pressure at B times the volume at B. Okay? And process from C to D is also isothermal. Right? So that's the contraction. Right? PC, VC. This is from an ideal gas law, by the way, right? Because this is isothermal. Is right, and process from B to C is adiabatic. PP to the power of gamma is equal to C to the power of gamma, and C to D is also adiabatic. T to C to D, T to A. Yes, I wrote it wrong here. T to A, yes. T to A is also adiabatic, so PD, phi to the power of gamma is equal to PA, VA to the power of gamma, right? And gamma is, from last week, is a specific heat in muscle pressure divided by specific heat in a constant volume. Okay? So this is all there is. And let's calculate the work. In fact, in reality, you don't have to calculate the work, right? It's easier to do it differently. It's kind of complicated to calculate the work because of that P to the power of gamma, right? But there's an adiabatic portion of it. But we know efficiency is given by W over QH. These are all positive quantity, by the way. Right? And this is just 1 minus QL over QH, right? All we need to do is calculate QH and QL during the isothermal process. QH is heat transfer during A to B, right? QL is the heat transfer during C to T. Okay? And we know for an isothermal process, U is 0, right? There is no internal energy change, so QH is equal to the work done from A to B, right? And we did this last week, and we found that this is equal to NK, NK is, of course, Boltzmann constant, H log of VV minus VA. Okay? And QL, right, is the work done from C to D, right? But I'm putting absolute values everywhere, by the way, because I just want positive quantity, right? I define the negative value explicitly, right? Then this becomes just N KB kilo, right? Because this is an isothermal contraction at the lower reservoir. Log of, in theory, it should be log of Vd over Vc, right? But since I'm putting absolute value, so that this is positive quantity, this is Vd, Vc over Vd. Vc is greater than Vd, so this is positive. Okay? So once I have that, then I have everything. Let me erase this part. From the condition of the adiabatic process, okay, let's see, from formula, what I erase it from this one. P to the power of gamma equal to PC to the power of gamma. I get, remember there's another equation for the adiabatic process. Instead of writing it as a P and V to the power of gamma, you write it as a PH V to the power of gamma minus 1. This is another equation for the adiabatic process, remember? It's equal to P low Vc to the power of gamma minus 1. Right? This is for the expansion. This is from C. And then there's another adiabatic process, which is from T to A, right? You get P to the power of gamma equal to A, VA to the power of gamma. This gives you pH, right? Because if you do the algebra right, This is PHVA to the power of 10 minus 1, right? This is the A point you will get. This is equal to T low, V T to the power of 10 minus 1, right? Is this clear? I should have filled this. Okay? Now I divide these two equations. I divide this by that, I divide this by that. Right? The TH cancels. Right? The kilo cancels. Right? Then I have VP over VA to the gamma minus 1. Okay? And it is equal to VC over VB to the gamma minus 1. Right? Okay? And the gamma is cancelled. Right? I'm left with that. Okay? So, let's calculate the efficiency. Efficiency is QL over QH, right? Then it becomes, oops, it's 10 o'clock. If you divide those two equations, right, then you have log of VC over VD divided by log of VB over VA. Right? Oh, sorry, no. I make a mistake, right? Where is the mistake? Okay, there is an M, K, T, L, right? And this is an M, K, T, H. Okay. Right? But now, because VB over VA is equal to VC over VD, this is the same, right? Sorry? Oh, yeah, sorry. 1 minus. Okay? One second, just 1 second. This cancel, right? I'm so bad at this. Okay? So 1 minus the NK cancel, right? So I'm just left with TL over TH. Okay? In my note, I have this, right? In my note, I didn't do it completely. In my note, I have that. This is also very important, right? In fact, this is more important, I think. So that's the reason I write it like that. And this is the efficiency of the Carnot engine. Okay. And then you can do a lot of problems with this. But that's not the whole point. The whole point, after all this long math, you can calculate the efficiency of a Carnot engine. We'll see next week why this is important, because this will lead to the concept of entropy, the second law in entropy, right? And it's one of the greatest discoveries of the 1800s, other than Maxwell. It's that, and it's all just from the consideration of a perfect engine by Carnot. It's mostly done by Carnot. Question? Sorry.